Here we look at how we can work out the equilibrium constant Kp. We've been given some information. We've said if a mole of A is added to a mole of B and at equilibrium 0.4 moles of C is formed, calculate Kp, and we are also given a total pressure. In order to do this, we need to set up a rise table, which you should be familiar with if you've been doing Kc calculations. The initial concentration, or the initial, moles of A is 1, the initial moles of B is 1, and as always, if we're not told the moles of my products, we assume it's 0. It says at equilibrium 0.4 moles of C is formed. So this moles of C has increased by 0.4, and that means that the moles of A and B, because it's a 1-to-1 mole ratio, must have both decreased by 0.4, which would give me 1 minus 0.4, which is 0.6 moles at equilibrium. So I've got my moles of each component in my equilibrium mixture at equilibrium. I'm going to now write an expression for Kp. Now, when we write an expression for Kp, we do not use concentrations. The concentration is replaced by something called the partial pressure, which is the pressure that each individual gas would exert if it was alone in the mixture. And that's represented by a P, and we say the partial pressure, therefore, of C divided by the partial pressure of A multiplied by the partial pressure of B. So partial pressure, that's what we need to put into my calculation for Kp. So how do I get from moles at equilibrium to partial pressure at equilibrium? First thing we need to look at is something called the mole fraction. That's the first thing we need to work out. So what is the mole fraction? Well, the mole fraction is equal to, I'm just going to write MF for moles fraction. Mole fraction of A is equal to the moles of A at equilibrium divided by the total moles at equilibrium. So we can see then the moles of A at equilibrium is 0.6. And the total moles at equilibrium is these added together. When you add them together, you get 1.6. And that gives me 0.375. And then we repeat the same procedure for each of my components in the equilibrium mixture. So I'm just going to copy this because it's basically the same. The mole fraction of B is exactly the same. We can see that it's also 0.375. Mole fraction of C, again, we work it out in the same way. But this time we've got, as you can see, equilibrium now, we've got 0.4. That gives me 0.25 as my mole fraction. So that's the first thing we need to do. We need to work out the mole fractions of each component at equilibrium. But we want partial pressure. How do we get partial pressure? Well, partial pressure we can work out by the following equation. Partial pressure is equal to the mole fraction times total pressure. Now, I've been told in the question that the total pressure is 100 kilopascals. So to get the partial pressure, I multiply each of these mole fractions by 100. And that gives me 37.5 for each of the A and B, and 25 for partial pressure of C's. And these would be in pascals, same or kilopascals, sorry, the same units as the total pressure is given in. And then it's a case now, it's these partial pressures here. These are the things that can be then plugged into your Kp expression. So Kp then will be equal to partial pressure of C, which is 25, divided by the partial pressure of A times B. Well, they're both 37.5, so say 37.5 squared. And when you do that, you end up with an answer of 0.0178. And this would be kilopascals. And we would say, because we've got 1 Pascal unit on the top, 2 Pascal units on the bottom, this would be kilopascals to the -1. And that there is your answer. So when you're doing these Kp calculations, a lot of the time you will have to do a right table working out the moles of each component in the equilibrium mixture. And then you need to convert them into a mole fraction, and then convert them into a partial pressure, and then put the partial pressures into your Kp expression. So the next video, calculating Kp2, will go through a slightly more difficult example.